Okay. Today we are going to discuss boundary layer theory. What is meant by boundary layer theory? I will tell you. What is meant by boundary layer theory? First, we'll draw one diagram. According to that diagram, we'll see. First, I will draw one solid boundary. Okay. Okay. This is what the velocity. Here, capital U. This capital U represent the free stream velocity. Free stream velocity. Okay. Now see, this is what one solid boundary. One solid object we are considering, and that we are immersed in a water at a certain level. So what will happen, we'll see one by one. Now see, you just imagine this solid object is immersed in water at a particular depth. Now see, this is what the free stream velocity. Now see, the direction of the flow is like this. Okay, the direction of flow is like this. Here, this is y and this is x. This x direction represent this is what the direction of flow. Now see, whenever the fluid is flowing in a particular direction, if suppose some object will be there, so what will happen exactly, we'll see that thing. Now see, first the water will strike here at this particular point, isn't it? Then what will happen, this dotted line okay, this is stream velocity, you just remember, because I don't have space here. Now see, whenever the water is strike on this point, what will happen, the velocity profile at this particular point, how it will come, like this. Okay. Now see, this distance here, for example, I will take infinity. So free stream velocity. So this free stream velocity, here also it is same. Here also it is same. Now see, at this particular point, the velocity is less. I will tell you how. Now see here it is 0, then 1, here it is 2, here it is 3, here it is 4. Okay, so here I will take 1, U2, U3, and here it is U4. Isn't it? So now see here the velocity will reduce like this, and up to this point that velocity will become a 0. Then now see, the direction of flow is like this. At this particular point, and this velocity, it is what? Local velocity. Okay, and this is free stream velocity. Now see here, this is local velocity. So here at this particular portion, u infinity equal to here I will assume v u phi is there. It means what? It is equal to 99%. It is similar to that free stream velocity at this portion. Okay, so this equation is most important, isn't it? Now this distance, it is denoted as del. Up to this point, this is what? Del. Okay, now see, this is del and we are representing this line is in y direction. Okay, now see here at this dotted line, represent the boundary layer or boundary layer, this dotted line, isn't it? Now see, this del represent, what is that? The thickness of boundary layer. Isn't it? And it is denoted as del. So now you understand what is meant by boundary theory. This dotted line represent, yes, boundary layer. Okay, and this del represent the thickness of boundary layer, isn't it? This equation is most important. Now you understand? Now what is meant by the boundary layer thickness? So this from here to here, that is your boundary layer thickness. Now see, after that we'll see some parameter. Okay, now see, here we'll consider a one plate. So what will happen, we'll see. So boundary layer is that thin layer of a fluid in the immediate vicinity of bonding surface over which velocity gradient and shear stress is large. Okay, so now see, what will happen, we'll see one by one. First, yes, we'll see, we'll consider one plate, and that plate we are immersed in a water at a particular distance. So what will happen in that portion, we'll see. Now say here, I will draw one plate. Okay, now you understand? And this is the profile. Okay. Now here I will draw, this is plate. Okay. Here this is one profile. Okay. I will do it like this. This is local velocity. At this particular point it is 0. This is velocity infinity. It means free shear velocity. Now here, what is this point? The boundary layer thickness, isn't it? So this is what? Boundary layer thickness. Then I will consider here one small element here. At this particular portion, I will consider small element, and that is, yes, dy. Because now see, the vertical distance or depth, that is, yes, y coordinate. This is y and this is x, isn't it? This is the direction of flow. At this particular axis, we are measuring depth. Okay, now see the object is what? Like this. Okay, after that, above, what will happen? That distance. So here I will consider dy. Okay, now again I will elaborate this diagram here. Then you can see that what will happen. This is what? One element. Now see here. Now this distance we are considered dy. Isn't it? If now see, at this element I will elaborate. This is what? One particular element. Isn't it? And this distance, that is b. Okay, we are considered element, isn't it? This is one element. From here we are elaborating. What will happen? We'll see. This is dy and this is b. Now see, the velocity will flow in this direction. Okay, so here we are considered u velocity. Okay, this is local velocity. Okay, one is infinity, that is free surface velocity or free stream velocity, or this is what? Local velocity with respect to this direction. Okay, and this is our element. Now after that we'll find out one small derivation that we'll see. Now here we calculate the mass flow rate per second. Here I will erase this diagram. Now you understand, and then later on I will tell you what happened. Here mass flow rate per second. How to calculate mass mass flow rate per second. Now see, here the density of water, here the area, here the velocity. Is that clear? Now see, if suppose we are providing some plate, so that time what will happen? Small u will be there. So here v equal to u and this v equal to infinity. This represent, here we are not providing a plate. Whatever the flow is with respect to that x direction, that only we'll consider. But if this v, this u represent what? We are providing some plate. Now what will happen? So now this is the parameter. First we will calculate this infinity, isn't it? We are not considering plate. Whatever the normal flow is there in a river or canal or anything, so that we'll consider. So here rho into area. What is that area? We are consider what? Element. Okay. This distance is what? B, and this distance is dy. So now see, B into dy, and this is u means u infinity. Okay, here we are not considering any plate. Okay, now second, if we consider that plate, again same formula, yes, area into velocity, but here rho into b as it is, area same, here only u will come because this portion, so we are consider what? This velocity, and here your velocity is u infinity and here it is u, and this is your plate. Now you understand? Now here what is the reduction, mass reduction per second? Now see, this minus this, so you will get what? The total mass reduction per second for whole boundary layer. So what is that? So total reduction mass per second for whole boundary layer, isn't it? So what is that? So now see, previous one, what is that? Rho b dy into u infinity minus again rho b into dy into u. So now see here, I will take this common, rho b, okay, then I will write infinity minus u bracket complete into dy. So this is your total reduction mass per second, isn't it? Then now we'll see what is meant by the boundary layer thickness? The boundary layer thickness represent what? It is del. Now you understand this? Total reduction mass per second. Okay. Before that, I will draw one diagram and then we will proceed or will discuss on next topic. This is very interesting. I will draw one diagram. Here now see, after this, then okay, here we provide some points for understanding point of view. Here it is A, here it is B, here it is C, here it is D. Now see here again, now see, this is what the laminar zone. Here it is transitional. And here it is turbulent. Turbulent zone. Okay. Now here, this is what laminar boundary layer. This is laminar boundary layer, and this point, that is leading edge. This is what the leading edge. Then and this is turbulent boundary layer. This is turbulent boundary layer and laminar sublayer. Sublayer. Okay. Now this is trailing edge. This is end of the. This is called trailing edge. Now see here, the laminar boundary layer means what? When a flat smooth plate is placed parallel to the direction of flow, the flow in the boundary layer is laminar, through the main flow is turbulent near to the leading edge of plate. This layer of the fluid is said to be laminar boundary layer. Okay. One more thing, here the Reynolds number we are consider, that is Re equal to Ux divided by viscosity, that is kinematic viscosity. Now see, this x distance represent from what? From here, okay, distance from the leading edge, that is represent x, and that u represent what? The free stream velocity. Up to this you understand? Okay. Now here this distance, that is your boundary layer thickness, isn't it? Okay, here the free stream velocity and here the local velocity, and this distance from this point to this point, that is boundary layer thickness. Now we'll see the displacement thickness with the help of one element. Now you understand, this is laminar zone, this is leading edge, this is boundary layer, laminar boundary layer, okay, this is turbulent zone, transitional zone. Here on this portion we will consider one element, and with the help of that element we will identify the displacement thickness. Okay, and then we'll see the derivation. It is very simple. Now first I will draw one diagram and then we'll proceed. Okay, here it is, your plate. Then here I will consider one element, okay, then this is y distance, depth. Okay, now this portion, that is your boundary layer thickness, now see here, this is your u, u infinity, because direction of the flow. Okay, now see, we'll consider one by one. First we'll see what is the displacement thickness. It is the distance perpendicular to the boundary by which the boundary should be displaced outward to compensate for reduction in the discharge in the boundary layer formation. So here now see, this formula represent the displacement thickness, and displacement thickness, it is denoted as del star. Now how to come this displacement thickness? We'll derive one equation. With the help of that equation we are able to solve, or we are able to prove that displacement thickness. Okay, now first consider the fluid flow having free stream velocity over a thin smooth plate. Okay, now see here in this diagram, consider the elementary strip at a distance y from here to here from the plate, and dy is the thickness. So now see this, dy, that is thickness. Now let u be the velocity at element strip and b is the width of the plate. Here we'll calculate mass per second through strip. So what is the mass per second here? Already we'll discuss mass per second equal to rho A into D. So here rho B into dy into into u. Here u represent u, capital U. Okay. So mass per second through strip, if no plate is placed, no plate is placed. Okay. Here. Okay. B dy into u. And the total reduction of mass per second of strip. What is that? Already we know that. Total reduction. What is that total reduction? Yes. Total reduction. Mass per second. So what is that? This minus this. So what you will get? Yes, rho B rho B in bracket u or u infinity. Here we are taking u infinity, so here it will be u minus u infinity. Okay, this is what? The total reduction. Now see, the total reduction of mass per second for whole boundary layer, we are integrate. Here I will erase some part. Now see, integration 0 to infinity delta. So here rho B u into du. Okay. Now let the plate displace by a distance. What distance? Del star, and the velocity of flow from the del star is free stream velocity, that is u. Okay. So here the loss of mass per second flowing through the distance del star, the loss of mass per second flowing through a distance del star. Okay, so what is that? We'll find out. Now here density into area into velocity. Okay. Now here rho, then yes, area. What is that area? B into del star into velocity, that is u. This is what? The loss of mass per second. Now we'll equate. This is equation number 1, for example, and this is equation number 2. So we'll equate this equation 1 and 2. So what we'll get, we'll see. So here, so rho into B into del star into u equal to that part, integration 0 to del or here we assume that that is what? Free stream velocity into du. If we equate this equation, so what we will get? We'll see. This will cancel, this will cancel, this will cancel, this will cancel, isn't it? So here del star equal to integration 0 to del. Okay. Here u minus small u divided by u into dy. Again I will simplify. Equal to integration 0 to infinity 1 minus if you simplify this, so you will get. So now see, this is your displacement thickness. Okay. After that, we'll see moment thickness. Now you understand? From this equation, it will come that form.